All right, engineers, grab your coffee, torque your nuts, and loosen up your tolerances. It's time for another episode of Mechanical Engineering Made Simple.
I'm really excited for this one.
Oh, me too. I mean, imagine you are sitting in gridlock traffic, right? Dead center on the Golden Gate Bridge.
It's just a terrifying thought on its own.
Yeah, exactly. You have thousands of cars stretching out in front of and behind you. Huge semi-trucks are rumbling by, the wind is howling off the bay, and this entire millions of tons structure is suspended above freezing, churning water by nothing but a web of steel cables.
Which, mathematically speaking, is perfectly fine.
Right. According to perfect mathematical theory, those cables should hold. We've all seen the clean equations on a whiteboard. But here is the terrifying secret we are going to explore today. Perfect materials just do not exist.
No, they absolutely do not.
Inside those massive steel cables are microscopic flaws, chaotic grain boundaries, jagged voids. I mean, the steel isn't perfect, it's a mess. So why aren't you plunging into the river?
Well, that is the million-dollar question, isn't it?
It really is. Welcome to today's custom-tailored deep dive. We are talking directly to you, whether you are an engineering student currently grinding through the brutal calculus of material mechanics or, a curious tinkerer who spends weekends rebuilding engines in the garage.
Or to someone looking up at a swaying skyscraper wondering why it doesn't snap.
Exactly. You are in the exact right place. We are going to peel back the polished exterior of the physical world.
It's always a privilege to take these journeys. The physical world we inhabit is unbelievably chaotic and complex.
It's incredibly messy.
Right. But the theoretical frameworks engineers have developed to tame that chaos, they're beautifully logical. The trick is getting past the initial intimidation factor of the raw mathematics to see the physical intuition underneath.
And our mission today is ambitious. We are diving into a massive, incredibly dense stack of foundational engineering reference materials.
Very dense.
We're bypassing the high-level summaries and going straight to the raw, heavy source data, spanning everything from basic area properties, glossary definitions, composite materials.
Stress concentrations, dynamic loads.
Yeah, and the terrifying suddenness of elastic stability.
Yeah.
But we aren't just going to read you equations. We're going to take this heavy textbook math and translate it into a fascinating, visceral exploration of how materials actually behave, why things break, and the clever mathematical tricks engineers use to keep the modern world intact.
Translating the math into physical reality is such a vital exercise. Too often in engineering education, the elegance of the equations completely obscures the messy physical reality they're supposed to represent.
Oh, totally.
So our goal for you today is to extract the tangible, physical why and how hidden deep inside those formulas.
Okay, let's unpack this. Before we can build a bridge, launch a satellite, or even, manufacture a reliable coffee maker, we have to deeply understand the fundamental nature of the physical materials we are using.
Absolutely.
But right out of the gate, we have to admit a bit of a dirty secret. Our foundational mathematical models, the very bedrock of structural engineering, they're built on what you might call a polite fiction.
Polite fiction captures it perfectly. When we sit down to calculate how much a steel beam will bend under a load, or how far a titanium shaft will twist in a jet engine, we rely on foundational concepts like elasticity, stress, and strain.
Right.
Let's define those in physical terms. Stress isn't just a general feeling of pressure. It is specifically the internal resisting force per unit area that the material exerts to fight back against being deformed.
Okay, so it's the material fighting back.
Yes. And strain, on the other hand, is the physical evidence of that fight. It is the forced change in the dimensions or shape of the material, a stretch, a compression, a shear distortion.
Got it.
And tying these two concepts together is Hooke's law, which essentially dictates that stress is perfectly proportional to strain.
So to put that in everyday terms, if you pull on a steel bar with 1,000 pounds of force, it stretches by, let's say, 1 millimeter.
Right.
And if you pull twice as hard, 2,000 pounds, it stretches exactly 2 millimeters.
Yeah.
It behaves like a perfect, predictable spring. You plot it on a graph, and it's a beautiful, clean, straight line.
Up to a specific threshold known as the proportional limit, yes. But here is where we introduce the fiction. To make this clean, linear mathematical analysis work, to derive the textbook formulas that engineers use every single day, we have to assume the material we are analyzing is flawless.
Which it never is.
Never. We assume it is perfectly elastic, meaning it returns exactly to its original shape with zero permanent deformation. We assume it is isotropic, meaning it has the exact same mechanical properties in every conceivable direction.
Oh, yeah.
We assume it is completely homogeneous, meaning it is perfectly uniform throughout its entire volume. And finally, we assume it is infinitely divisible, meaning no matter how microscopic a slice you take, the material properties remain perfectly constant.
Hold on, I have to push back on that because if I take a piece of structural steel, polish it up, and look at it under a powerful electron microscope, it is absolutely not a perfect uniform continuum.
Not at all.
It looks like a patchwork quilt. It's made of crystalline grains, jagged green boundaries, chemical impurities, carbon deposits, maybe even tiny microscopic voids where the metal didn't cast perfectly.
Exactly.
It is definitively not infinitely divisible. Eventually, you zoom in enough and you hit discrete vibrating atoms.
Yes, you do.
And if we look at a natural material, like wood, forget about it. Wood has a highly directional grain. It is wildly different in strength depending on whether you pull it along the grain or across it.
Extremely anisotropic, yes.
So if the math requires absolute perfection, but real-world materials are essentially chaotic and flawed at a microscopic level, aren't engineers just, well, guessing? It feels like we're assuming a lumpy, broken spring mattress is a perfectly flat, frictionless plane just to make the geometry easier to solve.
I love the broken mattress analogy because we can actually take it further.
Oh, please do.
Imagine you are trying to calculate exactly how a heavy bowling ball will roll across that broken mattress. If you wanted to do the math perfectly, you would have to map the tension of every single rusted spring, the exact tear in the fabric, the friction of the stuffing.
Which would take forever.
It is mathematically impossible. The variables are just too chaotic. So, engineers draw a flat mathematical plane over the mattress. We calculate the smooth roll of the ball on that fictional plane, and then we build in boundaries to account for the chaotic springs we intentionally ignored.
I see.
If we look closely enough at real materials, none of our pristine mathematical assumptions are strictly true. There is always some microscopic yielding, some tiny permanent deformation at the grain boundaries, some slight deviation from Hooke's perfect straight line.
So the math is just a model.
Exactly. What is truly fascinating here is how engineering bridges that massive chasm between a flawed physical reality and a perfect mathematical theory. We don't throw the math away. We use it to build heavily fortified boundaries around our own ignorance.
How do we actually build those boundaries in practice? If I'm designing a load-bearing pillar, I can't just guess how much the broken springs are going to affect it.
We handle it by establishing a rigid, uncrossable line between what we call the damaging stress and the allowable stress, which is sometimes called the working stress.
Okay, damaging versus allowable.
Right. The damaging stress is the brutal physical reality. It is the actual tested stress level that will physically render a part unfit for service. That might mean the pillar yields and visibly bends permanently, or it might mean a microscopic crack propagates into a catastrophic fracture from repeated fatigue.
So that's the absolute failure point.
Yes. But the allowable stress is a much, much lower ceiling artificially set by the engineer. We take the damaging stress and we drag it down, creating a buffer zone to account for the microscopic non-uniformity of the material, the inherent inaccuracies of our simplified stress analysis, and the unpredictable, chaotic conditions of real-world service.
We bake in a cushion. We say, I know the steel can technically hold 50,000 pounds per square inch before it permanently warps, but I'm going to pretend it can only hold 20,000 just to be safe.
That is the essence of it. But determining exactly when that material will fail in the real world, especially ductile, yielding materials like structural steel or aircraft aluminum, that requires a very sophisticated boundary called the maximum distortion energy theory, often associated with von Mises.
I've seen that term in the reference stack. Maximum distortion energy. It sounds like something from a sci-fi warp drive.
Yeah.
What does it actually mean for a piece of metal?
It addresses a fundamental flaw in how we think about pushing and pulling on things. If you take a cube of steel and you squeeze it perfectly evenly from all 6 sides...
Like dropping it into the deepest trench of the ocean.
Yes, exactly. It experiences immense hydrostatic pressure. But it won't yield. It won't permanently change its cubic shape. It will just temporarily compress into a slightly smaller cube. The energy that simply changes the volume of an object without changing its fundamental shape rarely causes ductile failure.
Because the atoms are just being pushed closer together equally from all sides. There's nowhere for them to slide out of place.
You've hit the nail on the head. Yielding Permanent deformation is entirely about atoms sliding past one another along slit planes. That only happens when the material is forced to change its shape.
Oh, that makes so much sense.
So the maximum distortion energy theory looks at the incredibly complex three-dimensional state of stress happening at a specific microscopic point inside a loaded part. It mathematically separates the energy that is just trying to change the volume from the energy that is actively trying to distort the shape.
Wow. It isolates the shape-changing energy.
Exactly. It isolates that pure distortion energy and compares it to the distortion energy present when a simple, standardized test specimen finally yields in a controlled laboratory test.
That is brilliant. We take a chaotic, complex, real-world load, maybe a bracket being twisted, bent, and pulled all at the exact same time, and we distill all that down to one number. How much is this trying to distort the shape?
That's it.
And if that distortion energy is less than what broke our test sample in the lab, we declare it safe.
It is an incredibly pragmatic way to predict failure in a lumpy, imperfect material using clean math. And this deep pragmatism applies to how we view load distribution across multiple parts, too. Let's look at something mundane, like rivets or bolted joints.
Sure, rivet.
The technical literature often discusses the concept of pure shear. In theory, if you have two heavy steel plates overlapped and held together by a single rivet, and you pull those plates in opposite directions, the rivet is subjected to pure shear, perfectly flat across its middle cross-section.
You're trying to slide the plates past each other like scissors, and the body of the rivet is the only thing physically blocking them. The force is trying to slice it horizontally right down the middle, like a piece of cheese.
That is the textbook theory. But the physical reality is that pure shear in mechanical joints is virtually a myth. The actual distribution of stress inside that rivet is chaotic. Think about the physical mechanics. The hole drilled in the plates is never perfectly cylindrical. The rivet expands to fill the hole, but never with absolute uniform pressure.
Oh, right.
As you pull the plates, they compress the sides of the rivet, causing localized crushing. The plates themselves bend slightly, which introduces tensile bending forces into the rivet, trying to pop its head off. Furthermore, the friction between the two steel plates actually carries a significant portion of the load before the rivet even engages fully.
That is a lot happening at once.
To calculate the true, exact stress on every single molecule of that rivet is mathematically indeterminate in everyday practice.
If you're designing an airplane wing with 10,000 rivets, you absolutely cannot calculate the micro-crushing and friction of every single hole. You'd never finish the airplane.
So we fall back on our polite fictions. We safely assume a perfectly uniform distribution of shear stress across the entire cross-section of the rivet. We take the total pulling force and we simply divide it by the circular area of the rivet. Force over area.
Even though it's not uniform.
We know it's a fiction. We know for a fact that the stress is significantly higher at the outer edges of the rivet than in the dead center. But we rely on applied safety factors, allowable stresses, and decades of physical destruction testing to ensure that our simplified fictional uniform stress is a rock-solid, safe design tool.
We rely on the fiction to do the math, and we rely on the safety factor to keep us alive.
Yeah.
I love that. Yeah. The math is just a map. It's not the territory. So since materials themselves aren't perfect and our loads aren't perfectly distributed, the physical shape of the part becomes the engineer's ultimate weapon.
Without a doubt.
If you can't change the atoms, you change the geometry. Let's move from material properties into geometric shenanigans.
Geometry is indeed where the structural engineer exercises their greatest control over reality. The reference stack provides an exhaustive breakdown of the properties of plane areas, specifically focusing on moments of inertia and principal axes.
For you listening, if you've ever flipped through an engineering manual, you've seen these pages. It's just endless charts of cross-sections, squares, hollow rectangles, T-sections, diamonds, hollow ellipses.
Pages and pages of them.
And they all have these complex formulas for something called the moment of inertia. I think this confuses a lot of people because in physics, moment of inertia usually refers to spinning mass, like a figure skater pulling their arms in.
A very common point of confusion.
But here, in structural mechanics, it's not about mass at all. It's purely about shape. It's a mathematical measurement of how the area of a cross-section is distributed away from its center bending axis.
The physical logic is quite elegant. When you bend a beam, the material right in the dead center, the neutral axis, doesn't stretch or compress at all. It experiences zero bending stress. But the material at the very top and the very bottom edges has to stretch and compress the most.
Right.
Therefore, the further away you move material from the center axis, the more leverage that material has to resist the bending force.
That is the exact reason why steel I-beams are shaped like an eye. They take almost all the heavy steel, the meat of the material, and put it in the top and bottom flanges, as far away from the center as possible. The thin vertical web in the middle is mostly just there to hold the two flanges apart.
Precisely.
If you took that exact same amount of steel and melted it into a solid square bar, it would sag under its own weight, but shaped into an I-beam, it can hold up a skyscraper.
The mathematics of shape beautifully dictate resistance to bending. But when we transition from bending to twisting, from flexure to torsion, the mathematics of shape become far less intuitive and, frankly, much more punishing.
The sources cover torsion extensively. Let's start with the easy stuff, twisting a perfectly round cylinder.
For a solid circular shaft or a hollow circular tube, the math is a joy to work with. When you apply torsion, the shear stress varies perfectly linearly. It is zero at the dead center of the circle, and it increases in a straight line until it reaches its absolute maximum at the outer surface. Most importantly, the cross-section of the cylinder remains perfectly flat as it twists.
I picture twisting a solid cylinder of perfectly uniform rubber. If you draw a straight grid on it, the grid just spirals smoothly, the flat ends stay flat.
But the moment you apply that exact same twisting force to a non-circular shaft, say a solid square bar, an I-beam, or a flat rectangular plate, the clean math breaks down entirely. The cross-sections no longer remain flat. They physically warp out of plane into complex three-dimensional curves.
Oh, wow.
The stress is no longer uniform, and it certainly isn't linearly distributed from the center. To solve the exact stress distribution for a twisting square requires advanced, highly complex theories of elasticity that involve nightmarish differential equations.
Here's where it gets really interesting.
Yeah.
Because the raw calculus for non-circular twisting is such a headache for everyday design, engineers in the early 20th century came up with a way to physically visualize the math instead of just crunching numbers.
Yes, they did.
Our sources detail something called the membrane analogy, or the soap film analogy. This is honestly one of my favorite concepts in all of engineering.
It was originally developed by the pioneering physicist Ludwig Prandtl, and it is a breathtaking conceptual leap. It maps a highly complex, invisible internal stress onto a visible physical phenomenon that we can intuitively understand.
Okay, if you are listening, I need you to picture this in your mind's eye. You're an engineer, and you need to know how a solid square bar is going to handle being twisted by a massive motor. The math is a nightmare.
A total nightmare.
So instead of doing the calculus, imagine you take a flat, rigid metal board, you cut a square hole in the middle of it, the exact same shape and size as the cross-section of your bar. Now, you dip that board in soapy water and stretch a delicate soap film perfectly over that square hole.
So far, so good.
Finally, you blow a tiny bit of air pressure underneath the board, causing the soap film to inflate upward into a slight bulging bubble.
And this inflation is not merely a fun visualization. It is an exact, rigorous mathematical analog. The differential equations that govern the physical shape, the bulging surface of that inflated soap film under pressure, are mathematically identical in form to the differential equations that govern the invisible torsional shear stress inside the solid twisted shaft.
Which means we can literally look at the physical shape of the bubble and see the invisible stress. The rules are incredibly simple once you map them out. The total volume of the inflated bubble, how much air is physically trapped underneath the soap film that represents the total torsional stiffness of the shaft.
Correct.
And the slope of the bubble at any given microscopic point, how steeply the soap film is angled relative to the flat board, represents the exact magnitude of the shear stress at that corresponding point on the real metal cross-section.
This raises a profound design question. If the slope of the soap bubble perfectly equates to the stress tearing at the metal, what does this analogy tell us about how we should design parts that need to twist? We want to minimize stress. Therefore, we want a bubble that is as gently sloped and as uniformly sloped as physically possible.
Let's test it. If you cut a perfect circle in the board and blow a bubble, it forms a beautiful, smooth, spherical dome. The slope is perfectly uniform all the way around the outer edge, and it's relatively gentle. That visually confirms what we already knew. A round shaft handles torque perfectly. But let's get weird. What if you need to design a shaft shaped like a star or a cross?
Visualize blowing a soap bubble over a star-shaped cutout. The soap film will bulge up in the wide center, but as it stretches out into the sharp, narrow points of the star, it won't inflate. The film in those outstanding points will remain almost completely flat, clinging to the edges of the cutout.
And according to our rules, a flat bubble means zero slope. Zero slope means zero stress.
Precisely the point. Outstanding flanges, sharp corners protruding outward away from the center of mass, they carry virtually zero stress during torsion. Therefore, they contribute almost nothing to the twinting stiffness of the part.
So they're just dead weight.
If you design a shaft with thick, protruding fins to make it look stronger, you are completely wasting material. The inner core is taking all the punishment while the outer fins do nothing. But conversely, turn your attention to the inner corners of that star or cross shape, the places where the arms meet the central hub.
Oh, the sharp concave inner corners. The bubble is bulging high in the center, but it has to instantly dive down to zero height to attach to that sharp inner corner of the cutout. The slope of the soap film right at that inner crease is incredibly steep, almost vertical.
And a steep vertical slope means massive, catastrophic, localized shear stress. This soap film analogy immediately tells the engineer a fundamental truth of the universe. Avoid sharp internal corners in any part subjected to torsion at all costs. The stress will spike to astronomical levels at that crease, and the part will tear itself apart from the inside out, starting exactly at that sharp corner.
This visual tool is just brilliantly pragmatic. You can literally see why certain shapes fail.
Yeah.
Look at a thin, flat, rectangular plate. If you cut a long, skinny slit in your board and try to blow a bubble over it, the soap film barely has room to inflate before it has to attach to the opposite side. The bubble is practically flat. Very little volume means very little torsional stiffness.
Exactly.
And our reference materials give a stunning, specific, numerical example of this geometric limitation. They compare a completely closed circular tube to a split-open tube.
The contrast is jarring. Imagine a standard hollow metal pipe. It forms a continuous, closed loop. In the soap film analogy, to model a hollow section, you don't just have a hole. You imagine a solid, weightless plate floating in the middle of the hole, perfectly matching the hollow inner void of the pipe. The soap film bridges the narrow gap between the outer edge of the hole and this inner floating plate.
Right, that makes sense for a tube.
When you apply air pressure, the air pushes the entire inner plate straight up, lifting the soap film with it.
As the plate lifts up, it creates a massive volume of empty space underneath the soap film and the plate combined. Massive volume equals massive torsional stiffness. A closed tube can carry a staggering amount of twisting force.
Now, take a hacksaw and cut a single tiny longitudinal slit all the way down the entire length of that pipe. Make it just 1 millimeter wide. You have removed virtually no mass. The pipe weighs exactly the same. To the naked eye, it looks functionally identical.
But geometrically, you have completely destroyed its torsional integrity.
You have compromised the continuous flow of stress. By making that tiny slit, you've turned a closed ring into an open C-shaped cross-section. Returning to the soap film analogy, if you try to pressurize that system now, the air simply escapes through the 1 millimeter slit. You can no longer pressurize and lift the inner floating plate. The immense volume vanishes. The bubble immediately collapses into a shallow, flat, weak film clinging only to the thin walls of the C-shape.
The theoretical math backs up this collapse with terrifying numbers. For the specific dimensions cited in the text, a tube with an outer radius of about 2 inches and a wall thickness of just 532 of an inch, the closed section is over 400 times stiffer than the split section.
400 times.
And is more than 30 times stronger before it yields.
A single millimeter cut results in a 400-fold loss in stiffness.
That breaks my brain. You lose a fraction of a percent of the material, but you lose 99% of the rigidity. But the soap bubble makes it instantly understandable. You break the continuous outer loop, you lose the trapped volume, you lose all the strength. The twisting force has to travel up and down the long way around the C-shape instead of just chasing itself in a continuous tight circle.
This profound vulnerability perfectly transitions us to the next reality of mechanical design. Geometry can absolutely save a design, as we see with the incredible efficiency of a closed tube. But localized microscopic geometry changes can absolutely doom it.
Right. A closed tube is a fortress. But what if you actually have to use it in a machine? You have to attach it to something. So you drill a small hole through the wall of the tube to put a mounting bolt through. Or maybe you need to thread the end of it to screw it into a bulkhead. Suddenly, you've introduced local geometry changes to your perfect fortress.
You have introduced what engineers call stress concentrations, or more colloquially, stress razors. Our sources dedicate significant analysis to calculating stress concentration factors, mathematically denoted as K-M. We discussed earlier how the nominal stress, the clean basic formula of force divided by area, assumes a smooth, continuous part. But the moment you introduce a sudden obstacle, a drilled hole, a sharp notch, a machine shoulder, or a screw thread, the internal stress cannot simply vanish. It has to flow around that obstacle, much like a fast-moving river flowing around a massive boulder.
I can picture that perfectly. In a wide river, the water moves calmly. But when it hits a boulder, the water has to compress and speed up to squeeze past the sides of the rock. It churns and creates rapids. The water lines bunch up. Inside a piece of steel, the invisible lines of force do the exact same thing when they hit a drilled hole. They bunch up tightly at the edges of the hole to get around it.
And where those force lines bunch up, the actual localized physical stress spikes to levels much, much higher than the average nominal stress of the surrounding material. AT is simply the mathematical ratio of that true localized maximum stress to the nominal calculated stress. If KT is 3, the stress at the edge of the hole is exactly 3 times higher than the stress an inch away.
That is a massive jump.
And these concentration factors can be severe, often dictating the entire lifespan of a machine. Let's examine screw threads, which are arguably the most ubiquitous fastening mechanism in human history. When you tighten a heavy nut onto a bolt, you are pulling the bolt into tension. How would you assume that massive pulling load is distributed among the threads hidden inside the nut?
Well, intuition tells me it's shared equally.
No.
If I have a heavy nut with 10 threads fully engaged on the bolt, it seems fair that each individual thread takes exactly 10% of the load. They all work together.
That is a highly logical yet incredibly dangerous assumption. Both advanced mathematical analysis and rigorous photoelastic physical testing reveal that the load distribution in a threaded joint is wildly, heavily unequal. The phenomenon is defined by the thread load concentration factor, denoted as H. We have to look at the microscopic elasticity of the metals to understand why.
Okay, let's zoom in.
As you tighten the joint, the body of the bolt is being pulled. It stretches and elongates slightly under tension. Conversely, the body of the nut is being pushed against the material. It compresses and shortens slightly.
Oh, I see it. The bolt is getting longer, but the nut is getting shorter.
Exactly. Because one is stretching and one is compressing, the physical distance between the threads, the pitch, actually changes slightly in opposite directions. The threads of the bolt stretch further apart while the threads of the nut compress closer together. This pitch mismatch means they can no longer share the load equally. The result is that the very first few threads located right near the loaded face of the nut, the point where the bolt first enters, are forced to take the absolute brunt of the force to bridge that microscopic gap.
How badly skewed is the distribution?
The engineering data explicitly states that this load concentration factor H is routinely 2, 3, or even 4. That means that the very first thread isn't taking its fair 10% of the load. It might be taking 2 to 4 times the average load. That single leading thread could be carrying 40% of the entire clamping force all by itself, while the threads at the back of the nut are practically doing nothing.
Wait, if you are changing your own tires, this means that the very first thread on your lug nut is doing almost half the work of keeping your wheel attached to your car at 70 miles an hour.
It is sobering to think about.
If you don't mathematically count for that massive concentration, that first thread yields and strips. Once it strips, it dumps all its load onto the second thread, which instantly overloads and strips, and the entire joint violently unzips in a catastrophic cascade failure.
A cascade failure is the precise danger. Furthermore, the root of the screw thread itself, the deep V-groove cut into the metal, acts as a sharp notch. As we learned from the soap bubble analogy, sharp inner corners create massive stress spikes on their own. So you have a notch geometry multiplying the stress, located exactly at the first thread, which is already carrying 40% of the load.
It's a double whammy.
This is why, when bolts fail from metal fatigue, the fracture almost invariably occurs directly at the root of the first engaged thread. It is the undeniable weakest link.
So we have to meticulously design around holes, notches, and threads. But let's push the geometric boundary even further. What about when two objects don't have a fastener at all? What happens when two solid pieces of metal simply press against each other? Think of a train wheel resting on a steel rail, or a tiny steel ball bearing rolling inside a motor casing.
We are moving into the realm of Hertzian contact stresses. This is the brutal, unforgiving physical reality of point-and-line contacts. In pure, pristine Euclidean geometry, a perfect sphere touching a perfect flat plane makes contact at exactly one infinitely small mathematical point. A cylinder touching a plane makes contact along one infinitely thin mathematical line.
But mathematically, Pressure or stress is defined as force divided by area. If they touch at a mathematical point, the contact area is zero. And dividing any force by zero gives you infinite stress. The universe can't handle infinite stress. The metal would just vaporize.
Precisely. The metals cannot maintain a theoretical point contact. They must physically deform. As the load is applied, the two curved elastic bodies compress and flatten out against each other, widening that infinitely small point into a small, finite area of physical contact, usually a tiny circle, an ellipse, or a thin rectangle. The intense, localized stresses generated inside this microscopic contact patch are called Hertzian stresses, named after Heinrich Hertz, the physicist who first successfully modeled them in the 1880s.
The sources bring up a fascinating application of this: knife-edge pivots. You find these in highly sensitive analytical balances in chemistry labs or in older mechanical scales. The goal is to have a razor-sharp wedge of hard metal resting on a perfectly flat plane, which reduces the friction point to near zero so the scale can balance perfectly.
It is a brilliant concept for reducing friction, but it runs headfirst into the Hertzian stress problem. A truly sharp microscopic knife edge simply cannot press against a flat plane without undergoing immediate plastic deformation. The theoretical stress at the tip is too high.
Right, infinite stress again.
The moment you place even a fraction of a gram of load onto it, the razor edge will invisibly crush, yield, and flatten out until a microscopic cylindrical surface is formed to carry the load. To maintain extreme accuracy and an analytical balance, the engineer must keep the pressures incredibly small. The sources note a specific boundary. To prevent excessive, ruinous deformation of the pivot, the radius of that supposedly sharp-loaded edge must be carefully machined to be kept under 0.25 millimeters, which is roughly 1/100th of an inch.
That's tiny.
If you try to machine it any sharper than that, the metal simply crushes itself flat under its own operational weight.
Let's take it to the extreme. Forget a delicate scale. What happens when you have two incredibly hard, strong objects forced together? Say, a hardened steel ball bearing violently pressing against a hardened steel plate.
The source data provides a window into this extreme environment by citing specific historical testing conducted by researchers Whitmore and Petrenko. They rigorously tested hardened steel spheres pressing against flat steel plates to determine the exact elastic limit, the precise microscopic moment where the sphere begins to permanently dent the flat plate. They found that the required Hertzian stress to cause that permanent dent is astonishingly high.
Give me the raw numbers. How high does the stress get in that tiny contact patch?
The crushing load corresponds to a calculated Hertz stress of approximately 4 Melsennellen multiplied by the diameter of the sphere to the power of -112.
Let me stop you there. 4 million. Standard structural steel yields at what, 36,000 psi? High-strength titanium might yield at 150,000 psi. You were talking about millions of pounds per square inch of stress. Why doesn't the steel simply turn to dust or shatter like glass?
It is a phenomenal question, and the answer lies in the concept of triaxial compression. We have to visualize the microscopic reality directly under that tiny contact patch. The steel atoms situated exactly at the point of contact are experiencing millions of pounds of downward pressure. They desperately want to escape that pressure by flowing plastically outward, squishing to the sides like stepping on a piece of clay. But they can't.
Because they are completely surrounded by the rest of the solid steel plate.
Exactly. The atoms directly under the load are trapped. The massive expanse of unstressed, solid steel surrounding that tiny microscopic point acts like an unbreakable, rigid corset. As the atoms under the load try to bulge outward, the surrounding steel pushes back inward with equal ferocity. This restricts the atoms from sliding along their slip planes. Yielding, as we discussed with the distortion energy theory, requires a change in shape. But because the material is confined equally from all sides, it is locked in a state of triaxial compression.
Triaxial compression.
Yes. It cannot change shape, so it cannot yield. It allows the metal to withstand astronomical localized compressive stresses that are orders of magnitude higher than its normal unconfined yield strength.
That is just mind-blowing. The material is screaming, trying to squish outward, but the geometry of the surrounding bulk material simply says, no, you don't, allowing a tiny steel ball bearing to carry massive loads without disintegrating.
It is a beautiful mechanical phenomenon. However, it has limits. If the load is too high, or more commonly, if that massive Hertzian stress is repeated millions of times, as it is in the rolling teeth of a gearbox or the spinning balls of a wheel bearing, the crystalline structure of the metal will eventually suffer subsurface fatigue.
Ah, Fatigue.
Microcracks will form deep below the contact patch, propagate to the surface, and chunks of metal will violently flake off in a process called pitting or spalling. Deeply understanding Hertzian triaxial stress is the only reason engineers can design gears and bearings that roll smoothly for years without destroying themselves.
Okay, we've taken a deep look at uniform metals. We've seen how geometry can act as a fortress or a fatal flaw. We've seen how metals survive, touching each other under millions of pounds of pressure. But what happens when engineers get tired of working around the inherent limitations of metal? What happens when we intentionally mix wildly different materials together to cheat the physics of geometry entirely? Enter the future of engineering. Composite materials.
The reference materials dedicate an entirely separate framework to composites, and for good reason. It represents a fundamental paradigm shift in how we conceive of structure. With traditional metals like steel or aluminum, as we discussed, we safely assume they are isotropic. If you pull a block of aluminum up, down, left, right, or diagonally, it pushes back with the exact same strength and stiffness. It is uniform. Composites, however, are fundamentally anisotropic or profoundly directionally dependent.
When we talk about composites like carbon fiber, fiberglass, or Kevlar, we're talking about materials built from two distinct separate components, right? The reinforcements and the matrix.
Correct. You have the reinforcements, which are typically continuous, microscopic fibers of carbon, glass, or aramid. These fibers are incredibly strong and stiff, but only in tension and only along their length. You can think of them like microscopic ropes, but you cannot build an airplane out of loose ropes. You need the second component, the matrix.
Right, you need something to hold
The
them.
matrix is typically a plastic polymer resin, like epoxy. Its job is to encase the fibers, hold them in a specific geometric shape, protect them from the environment, and critically, transfer the physical load from one fiber to the adjacent fiber through shear force.
So you have these incredibly strong carbon fibers running in one specific direction, locked in cured epoxy. That means the resulting material is unbelievably strong if you pull it perfectly straight in the direction of the fibers. But what happens if you pull it sideways?
That extreme directional vulnerability is the crux of composite design. The mathematical models define this using distinct moduli. You have an E1 modulus, which defines the longitudinal stiffness directly parallel to the fibers. This stiffness is dominated by the carbon itself, so it is exceptionally high. But then you have the E2 modulus, which defines the transverse stiffness perpendicular to the fibers. When you pull sideways, the load isn't being carried by the strong carbon ropes. It is tearing directly at the relatively weak, soft epoxy matrix holding the ropes together. The E2 stiffness is therefore drastically lower.
To give a visceral analogy, a single layer, a ply of composite material, is a lot like a bundle of dry, uncooked spaghetti held together with dried jello.
That is quite the image.
If you pull the spaghetti straight from the ends, it's remarkably hard to break. But if you pull the bundle sideways, the jello simply splits down the middle with almost no effort.
A slightly absurd analogy, but mechanistically accurate. Because the transverse properties, the sideways strength of the jello, are so incredibly low, practical, real-world composite structures are almost never manufactured with the fibers running in just one single direction. A single-direction wing would snap off the moment the wind hit it from an odd angle. So composites are built up layer by layer from a stack of individual thin plies, creating a laminate. Each individual ply in the stack is rotated to a different specific angle, some at 0 degrees, some at 45, some at 90, creating a web of strength designed to handle loads from multiple different directions.
And this is where the engineering math must get completely wild. Because now you aren't just analyzing one block of uniform material, you are analyzing a towering stack of different materials, essentially, because a ply rotated at 45 degrees behaves completely differently under a vertical load than a ply oriented at 0 degrees.
It requires an entirely distinct, massive mathematical framework called classical laminated plate theory, or CLPT. The central premise of CLPT relies on a fascinating interplay between continuous geometry and discontinuous physics. In CLPT, we assume that when a composite panel bends or stretches under a load, the physical strain, the actual geometric stretching of the panel, remains smooth, continuous, and linear completely through the entire thickness of the stack.
Okay, let's visualize that. The panel bends smoothly into a curve. The layers aren't delaminating or physically sliding past each other like a deck of cards. They stay glued together and deform as one single cohesive unit.
Exactly. The physical strain is smooth, But, and this is a massive counterintuitive but, because every single ply in that glued stack has been rotated to a different angle, every single ply possesses a drastically different modulus, a different stiffness in the direction of the bend. Recall Hooke's law from the very beginning of our journey. Stress equals strain multiplied by the modulus of stiffness. If the geometric strain is smoothly continuous, but the inherent material modulus jumps wildly as you cross the boundary from a 0-degree ply to a 90-degree ply,
Then the resulting stress inside the material must jump wildly from ply to ply.
you've deduced the core weirdness of composites. The internal stresses are physically discontinuous at the microscopic ply boundaries. Within the microscopic thickness of one single ply, the stress varies smoothly. But the exact nanosecond you cross the glued boundary into the next ply oriented at a different angle, the stress profile violently spikes upward or plummets downward.
That is deeply counterintuitive if you are used to working with metals. In a thick steel beam, if you graph the stress from top to bottom, it's a smooth, beautiful diagonal line. But if you graph the stress through a carbon fiber composite panel, it looks like a jagged, chaotic staircase.
This severe discontinuity is precisely why analyzing composite structures by hand is nearly impossible, and why engineers rely entirely on massive computer matrices. But the theoretical implications derived from CLPT are what we truly care about. The theory introduces three fundamental stiffness matrices that govern how the composite behaves: A, B, and D.
Let me check my notes on this because it gets deep. The A matrix defines the in-plane stiffness, basically how hard it is to stretch or shear the panel flat. The D matrix defines the bending stiffness, how hard it is to physically flex or twist the panel out of plane. But the B matrix, the reference material is called B, the membrane bending coupling matrix. I had to reread this section 3 times. Are they saying that if I take a flat composite panel and pull on it perfectly straight, it might magically decide to twist or warp out of shape all on its own?
What is genuinely fascinating and often infuriating for young engineers is that, yes, if the mathematical B matrix of a laminate is non-zero, purely pulling on the panel in a straight line will generate internal moments that cause the panel to physically warp, curl, or twist out of plane. Or, acting in reverse, if you apply a pure bending moment trying to fold the panel in half, the panel will simultaneously stretch or shrink in length. The forces are completely coupled together.
That is absolute madness. If I hang a heavy engine from a flat carbon fiber plate, the plate might just curl up like a potato chip under the tension. It reminds me of building furniture with cheap, poorly glued plywood. If the grains of the wood layers are fighting each other, the moment the humidity changes, the whole sheet just warps and cups into a bowl on its own.
That is an excellent physical parallel. In fact, the source texts make a direct structural comparison to bimetallic strips, which are discussed in a different chapter. A bimetallic strip, the kind used in old mechanical thermostats, is made of two different metals fused together, each with a different rate of thermal expansion. When the strip heats up, the brass side expands faster than the steel side, forcing the entire flat strip to curl into a tight bend. A composite panel with a non-zero B matrix does the exact same thing, but it doesn't need temperature to do it. It curls strictly under physical, mechanical stretching.
That sounds like an absolute nightmare if you were designing a high-performance machine. You design an airplane wing to stretch slightly upward under lift, and instead the B matrix causes the wing to violently twist, ripping the aerodynamic shape apart and stalling the plane.
Such coupling is highly undesirable in the vast majority of structural applications. So how do engineers solve this inherent material flaw? They cheat the geometry by strictly dictating the stacking sequence of the plies. If you meticulously ensure that for every single ply located on the top half of the laminate's midplane, there is an exact, identical ply of the same material, the same thickness, and the same angle placed at the exact corresponding distance on the bottom half of the midplane.
You build it as a perfect mirror image of itself, top to bottom.
Yes. This is mathematically defined as a symmetric laminate. If a laminate is perfectly symmetric, the entire complex B matrix instantly mathematically cancels itself out to identically zero. The stretching forces and the bending forces become completely uncoupled. Pulling the panel only causes stretching. Bending the panel only causes curving. Sanity is restored to the geometry.
Oh, there's a beautiful, elegant fix. Just mirror the stack and the chaos cancels out.
It solves the bending problem, yes. But you still might have coupling between stretching and shearing. If you pull the panel perfectly straight, it might skew sideways into a parallelogram. To eliminate that coupling, engineers must make the laminate balanced, meaning for every single ply angled at, say, positive 45 degrees, you must include a corresponding ply somewhere in the stack angled at negative 45 degrees to fight it.
So to force this wild anisotropic composite beast to act like a normal, predictable, sane material, you have to meticulously design a balanced, symmetric laminate stack.
Exactly. And structural engineers often take it one step further. By arranging the plies in very specific, symmetric, balanced angular distributions, most commonly 0 degrees, positive 45, negative 45, and 90 degrees, you can synthesize what is called a quasi-isotropic laminate.
Quasi-isotropic.
Yeah.
So by stacking the layers perfectly, you trick it into acting like an isotropic material, like a solid sheet of steel or aluminum that is equally strong in all directions.
In terms of its in-plane stiffness, yes. It tricks the highly directional layered composite into behaving macroscopically like a uniform metal panel. This allows engineers to design complex composite structures using much simpler, more familiar isotropic mathematical rules. It is a profound triumph of mathematical arrangement over inherent material limitation.
I absolutely love that concept. We tame the chaotic material simply by stacking it into a perfect mathematical mirror. So let's take a breath and figure out what all of this means so far. We've established boundaries around flawed yielding materials. We've optimized shapes using soap bubbles to visualize torsion. We've navigated the treacherous waters of stress concentrations and millions of pounds of Hertzian point pressure. And we've learned how to layer composites to cheat physics. But everything we've talked about up to this point has been mostly static, things sitting still, being pulled or pressed. The listener knows that the real world moves. Jet turbines spin at tens of thousands of RPMs, car suspensions bounce violently, airplane wings batter through chaotic turbulence. How does violent movement change the mathematical rules?
Movement introduces dynamic stresses and the terrifying prospect of geometric instability. Let's begin with pure movement. The reference stack delves deeply into the mechanics of rotating disks, which covers everything from the massive flywheels in a power plant to the titanium turbine blades inside a jet engine, down to the brake rotors on your car. When a solid disk rotates at high speed, every single microscopic molecule of that material is experiencing a violent centrifugal force trying to pull it outward, away from the center axis.
It's essentially trying to tear itself apart, tear its own arms off, just by the sheer act of spinning.
Precisely. This outward pull generates massive radial and tangential tensile stresses stretching the metal. The governing equations are complex. They depend on the material's Poisson's ratio, its physical mass density, and crucially, the square of the angular velocity. But hidden deep inside this complex math is a beautiful, deeply counterintuitive geometric quirk that the sources specifically highlight.
Lay it on me. I love counterintuitive physics.
Imagine you have two disks that are geometrically similar, exact scaled replicas of each other. One is a tiny, delicate turbine disk the size of a teacup saucer. The other is a massive, scaled-up exact replica the size of a two-story house. If they are machined from the exact same material and they are spun up so that they run at the exact same peripheral velocity, meaning the outer edge of both disks is traveling through the air at exactly 500 miles per hour.
Okay, let me visualize this. The massive house-sized disk is spinning at a very low RPM, turning slowly, but because it's so huge, its outer edge is sweeping through the air at 500 mph. The tiny saucer disk is screaming at tens of thousands of RPMs to get its tiny edge going 500 mph.
Correct. Under those exact conditions, the math reveals that the two vastly different disks will be equally stressed at all corresponding internal points. The stress at the center hole of the saucer is identical to the stress at the center hole of the house-sized disk.
Wait, let's pause. I don't buy that immediately. The house-sized disk weighs hundreds of tons. There is so much more physical mass pulling outward, generating centrifugal force. How can the stress not be astronomically higher in the massive disk?
It is a brilliant mathematical cancellation. You are correct that the massive disk has drastically more mass, which means it generates drastically more total centrifugal force. The force scales up with the volume of the material. However, physical stress is defined as force divided by area. As you scale up the disk, the cross-sectional area of the metal available to carry that massive force also scales up in the exact same proportion. The massive increase in pulling force is perfectly, elegantly canceled out by the massive increase in the thickness of the metal holding it.
That is fascinating. The physics perfectly scales.
Furthermore, the rules of rotating disks allow you to change the axial and radial dimensions independently without breaking the rule. You can take that disk and make it twice as thick, or machine it twice as wide, and as long as you maintain the exact same peripheral velocity at the outer edge, the internal stresses at similarly situated points do not change by a single psi.
I can instantly see why that is incredibly useful for engineering design and prototyping. You don't have to build a multi-million-dollar house-sized turbine disk just to see if it will explode. You can machine a tiny cheap saucer out of the same titanium, put it in a lab, spin it up until the edge is doing 500 miles an hour, measure the stress, and know with absolute mathematical certainty exactly how the giant version will behave at 500 miles an hour.
It is a profound money-saving shortcut in aerospace and power generation design. But dynamic situations also lead to catastrophic failures that have absolutely nothing to do with the material yielding, stretching, or fracturing. They are failures where the physical geometry simply gives up. We are talking about elastic stability, commonly known as buckling.
Buckling. This is the classic empty soda can trick. You take an empty aluminum can, you stand on it, and it easily holds your weight. The very thin aluminum is strong enough in pure compression. But the moment you tap the side of the can with a pencil, the sides suddenly crease, fold inward, and the whole thing violently collapses flat in a fraction of a second.
That is a perfect physical demonstration. Buckling is not a failure of material strength. It is a failure of geometric stability. It occurs almost exclusively in structural members that have a very large length compared to their lateral width, like long, slender collars, tall pillars, or thin-walled cylindrical tubes when they're subjected to heavy compressive stress. The aluminum in your soda can was nowhere near its ultimate crushing strength. It could theoretically hold hundreds of pounds, but the geometry became unstable and snapped through to a lower energy state.
Our reference materials spent a lot of time on the math of this, specifically discussing the Euler formula and the secant formula for predicting when columns will buckle.
Yes. The Euler formula is the foundational theory. It calculates the critical buckling load for a perfectly straight, perfectly loaded, infinitely long, slender column. What is remarkable about Euler's formula is what is missing from it. It depends entirely on the geometric moment of inertia of the cross-section and the modulus of elasticity of the material, how stiff it is. It does not factor in the compressive yield strength of the material at all.
Because the column will bow out and snap long before the molecules ever get crushed enough to yield.
Exactly. But Euler's formula brings us crashing back to our polite fictions. There is no such thing in the physical universe as a perfectly straight column. And there is no such thing as a load applied perfectly, flawlessly down the dead center of the axis.
If the load is off by a millimeter, it starts to bend the column slightly, which introduces a bending moment, which causes it to buckle even faster.
Which is precisely why engineers developed the secant formula. The second formula introduces an eccentricity ratio. It explicitly assumes that the load is slightly off-center or that the column has a slight initial crookedness from manufacturing. By assuming a realistic, measured imperfection, calibrated by decades of crushing actual structural steel columns in laboratories, the secant formula predicts failure loads that safely match the messy reality of construction sites, rather than the pristine perfection of Euler's chalkboard.
But the reference texts issue a pretty stark, almost frightening warning when it comes to buckling, specifically regarding thin-walled tubes.
Yes, and this is critical for aerospace design. The texts provide beautiful theoretical formulas for calculating the critical stress that causes thin-walled cylinders, like rocket bodies or airplane fuselages, to buckle under compression or twisting torsion. But the text explicitly, heavily warns the engineer that the critical stress indicated by the clean theoretical formula must be regarded strictly as an upper limit.
An upper limit, meaning the math tells you the absolute maximum it could possibly hold, but in reality, it will definitely fail before you reach that number.
Often disastrously before. The mathematical theory assumes a perfectly cylindrical tube. But real-world manufactured tubes have tiny, imperceptible dents. They have microscopic variations in wall thickness. They have slight out-of-roundness from being transported. In the mechanics of thin shell buckling, these microscopic geometric imperfections do not just add a tiny bit of extra stress, they act as catastrophic triggers. They initiate a localized geometric crease that spreads at the speed of sound, causing a complete structural collapse at loads that might be 30, 40, or even 50% below what the perfect theoretical formula predicted. For a thin tube under heavy compression, relying purely on the theoretical formula without massive tested knockdown factors is highly dangerous engineering.
So what does this all mean? It means that engineering math isn't absolute gospel truth. The math is just a boundary drawn around the terrifying unknown. We use Euler to find the absolute maximum theoretical limit of the universe, and then we use the secant formula and empirical knockdown factors to map out where the monsters actually live in reality.
That is an exceptionally accurate synthesis. The vast, murky gap between perfect theory and flawed reality is where actual engineering takes place.
Which brings us perfectly to our final section, the engineer's safety net. Let's recap the horrors we've uncovered. The materials aren't perfect, they're full of chaotic grains. The geometric loads are dynamic and tearing things apart from the inside out at stress concentrations. And the theoretical math sometimes wildly overestimates how strong a structure actually is. So how do engineers actually trust their designs? How do we build bridges, launch humans into space in thin metal tubes, and sleep soundly at night when we know the math is built on assumptions that aren't strictly true?
We survive by utilizing rigorous, overarching analytical principles to double-check every step of our work, and we employ absolute, unyielding pragmatism when the math fails to give us a clear answer. The sources outline these fail-safes beautifully. One of the most powerful, yet conceptually simplest tools for checking complex formulas is dimensional analysis.
Dimensional analysis, that's just making sure the units balance out, right? Like making sure you don't add apples and oranges.
It sounds trivial to a layperson, but it is profoundly important in preventing catastrophic errors. An equation must be dimensionally homogeneous. You simply cannot add inches to pounds. You cannot equate a unit of force to a unit of temperature. Every single term in a complex equation must mathematically resolve down to the exact same physical units. The text gives a fantastic, highly detailed example of using dimensional analysis to reverse engineer a seemingly magical empirical coefficient that a lot of young engineers just blindly memorize.
Oh, the 2592 example. I love this part.
Go.
Let's walk the listener through this because it shows how engineers hack math to make their lives easier on the job site.
The text posits a standard empirical formula used for calculating the deflection of a beam under a distributed load. The baseline theoretical equation is deflection equals a constant c multiplied by the load, multiplied by the length to the fourth power, all divided by the modulus of elasticity E and the moment of inertia I. Standard textbook beam theory.
Right. And in pure theory, the constant c is a clean fraction, usually 18.
But the text notes a practical problem. In the real world of American construction, engineers often measure the length of a beam in feet because saying a beam is 20 feet long is easier than saying it is 240 inches. However, the load is measured in pounds per inch, and the material properties E and I are always in inches. If you plug a length measured in feet into a formula expecting inches, you have a severe dimensional mismatch. The answer will be dangerously wrong.
Because you are violently mixing feet and inches in the same formula. It's like trying to bake a cake using Celsius for the oven, but Fahrenheit for the recipe book.
Exactly. To make the formula work seamlessly for the engineer in the field, the constant c can no longer be the theoretical 18. The constant itself has to silently absorb the unit conversion so that the final deflection answer comes out correctly in inches, even if the user typed in feet.
Okay, let's do the actual math for the listener because it's so satisfying when it clicks. We want the final answer in inches. The load is in pounds per inch, but the length L is in feet. To convert that length to inches inside the formula, we have to multiply it by 12. But the length term is raised to the fourth power. So it's not just times 12. It is feet times 12 to the fourth power.
Precisely. If we trace the dimensions, we have inches equals 18 multiplied by pounds per inch multiplied by feet times 12 to the fourth power, all divided by the denominator, which resolves to pounds times inches squared.
So to find our new magic constant, we have to pull that 12 to the fourth out of the parenthesis and combine it with the original 18. 12 to the fourth power is exactly 20,736. And 20,736 divided by 8 is exactly 2,592.
Yes. Dimensional analysis effortlessly reveals why the empirical coefficient found in so many engineering handbooks must be 2592 instead of the theoretical 18. It isn't a magical, arbitrary number handed down from the heavens. It is just a mundane unit conversion hidden inside a constant to make the engineer's life easier when they want to quickly plug in feet and get out inches. If an engineer forgets this history and accidentally plugs inches into a formula specifically designed to accept feet, a quick dimensional sanity check will flag the massive error immediately. The units simply won't balance.
That is a brilliant sanity check. You can trace the DNA of the formula just by looking at the units. But what about situations where you don't even know the inputs to begin with? For example, you're designing a steel beam for a balcony. You don't know exactly how the construction crew is going to bolt it to the wall. You don't know if the connection is going to act like a perfectly rigid, unmoving fixed support, or if it will flex and rotate a bit, acting like a loose pin support. The math for those two scenarios is completely different. How do you design it if you don't know how it will be built?
That is where the ultimate brute force pragmatic hack comes in. Bracketing assumptions.
I absolutely love this method. This is the ultimate cover your bases strategy. You don't know if it's fixed or pinned. so you don't guess.
You refuse to guess. You calculate both extremes.
Exactly. You sit down and run the entire massive mathematical calculation, assuming the beam is perfectly rigidly fixed to the wall. You find the maximum stress. Then you wipe the chalkboard clean, and you run the entire massive calculation a second time. This time, assuming it is perfectly freely pinned and rotating. You know for a fact that the messy reality of the construction site has to lie somewhere in the middle between those two theoretical extremes. If you design the steel beam so that it is thick enough and strong enough to comfortably survive both extreme conditions, it mathematically doesn't matter what the construction crew does. It's safe regardless of reality.
If we connect this to the bigger picture of our entire discussion, engineering is not the pursuit of absolute physical truth. It is the art of safely bounding human ignorance. We cannot know everything. We cannot map the microscopic grain of every single piece of steel or calculate the exact crushing friction of every rivet or predict the precise accidental dent a forklift might put into a thin aluminum tube.
So, because we are ignorant, we rely on the final safety nets, the margin of safety and the factor of safety.
Yes. The glossary defines these concepts beautifully, as they are the very bedrock of public safety. The factor of safety is simply the ratio of the load that would theoretically cause the part to fail, divided by the maximum load it is ever expected to see in actual service. If we calculate that a bridge beam will yield and fail at 30,000 pounds of force, but the heaviest truck allowed on the bridge only exerts 10,000 pounds, we've built in a factor of safety of 3.
We overbuild it by 3 times just to cover our polite fictions. And margin of safety.
Margin of safety, which is heavily used in aerospace where you can't afford to overbuild things too much because of weight, is the percentage by which the ultimate tested strength of the part exceeds the required design load. A design load which, by law, already includes a base safety factor. These layered numerical factors bridge the gap between our pristine, flawless mathematical models and the messy, unpredictable, chaotic real world. They account for every single polite fiction we have discussed today.
It really brings it all full circle. Our math isn't reality. But by using aggressive safety factors, brute force bracketing, dimensional sanity checks, and a deep intuitive understanding of how physical geometry manipulates invisible stress lines, we can build a physical reality that survives our own ignorance.
It is the ultimate triumph of applied science and pragmatism over pure, fragile theory.
Okay, let's take a breath and recap this incredible journey we just took. We started by shattering the illusion of perfect materials, learned that Hooke's law is a necessary lie, and seeing how von Mises uses distortion energy to predict when the chaotic grain structure of steel will finally yield. We moved into the magic of geometry, using Prandtl's brilliant soap bubble analogy to visually understand why sharp inner corners are a death sentence, and why a tiny 1 mm slit in a tube destroys its ability to handle torsion, causing a mind-boggling 400-fold loss in stiffness.
We then zoomed in on the severe stress concentrations lurking invisibly in the very first thread of a common nut and bolt, and explored the terrifying multi-million psi Hertzian triaxial stresses generated when a tiny, hardened steel sphere touches a flat plate, held together only by the corset-like confinement of the surrounding metal.
We looked at the anisotropic future with composite materials, discovering how the soft jello of the matrix transfers shear to the strong spaghetti of the carbon fibers, and how layered carbon can magically warp like a cheap, wet piece of plywood if you don't perfectly mirror image the stacking sequence to cancel out the dreaded B matrix. We saw how the dynamic scaling law allows a tiny disk to predict the stress of a massive turbine, how buckling math for thin cylinders is just an upper limit warning, not a guarantee, and finally, how engineers use unit conversion hacks, bracketing, and safety factors to sleep soundly at night.
A comprehensive, visceral tour of the mechanics of materials. So, to you listening, the next time you are sitting in traffic on a suspension bridge or flying through turbulence in a composite airplane, or even just stepping on a highly precise digital scale in your bathroom with a tiny knife-edge pivot inside, take a moment to remember what is actually going on underneath the surface. You are trusting your life to this exact, incredibly complex matrix of mathematical assumptions, brilliant geometric optimizations, and brute force pragmatic safety factors. You're trusting the polite fiction, backed up by decades of rigorous, unforgiving engineering boundaries.
It is a remarkable, deeply human system of thought to rely upon.
It really is. But before we sign off, I want to leave you with one final mind-bending concept pulled directly from the source material that we didn't get to fully unpack today: residual stresses and pre-stressing.
Ah, yes. A fascinating physical paradox to end on. Think about everything we discussed today. We spend the last hour meticulously trying to figure out how to lower stress, how to smooth it out, how to avoid it.
Right.
But sometimes, engineers will intentionally aggressively induce massive, near-breaking stresses into a material before it is ever even used in service. The reference texts explicitly detail processes like wrapping steel wire under immense screaming tension around a thick inner cylinder, like a high-pressure pipe or an artillery gun barrel, or thermally shrinking a massively tight outer metal jacket onto a cold inner tube. By doing this, you are intentionally crushing the inner material, pushing it right to the absolute brink of yielding before you've even turned the machine on.
You are inducing deliberate, calculated damage to the structure.
Exactly. I want you to mull this over on your own. How in the world can introducing internal damage or massive, crushing pre-stress actually make a system infinitely stronger and safer against massive external forces, like the explosive outward pressure of a firing artillery shell? It seems completely backward to everything we just learned. It seems like you're helping the explosion destroy the barrel. But it's actually one of the most powerful, elegant tricks in the entire engineering playbook. Ponder that mechanical paradox. Thank you for joining us on this massive deep dive. Keep questioning the physical structures around you, keep looking for those dangerous, sharp inner corners, and always keep loosening those tolerances. We'll see you next time.